All right, so hello. I'm Russell. I've worked at AOS for a while, and my main job is pretty much to make Rust teams successful. So whatever needs to get done, that's my team's job. One of the hats that I wear a lot is the person that gets DM'd when someone thinks that it's Tokio's fault that their service is slow. And about the 10th time that happened, it seemed like I should try to obsolete myself out of this process. So that's why I'm here. I ended up building a tool with one of my coworkers, Jess, called dial9. And the hypothesis is that what if we build a system that it was efficient enough to record individual events that you could basically run it in prod and record everything? Because if you actually had all this data, you would be able to look back and it would become pretty much obvious what the problem was. Okay, all right. So I know at the workshop yesterday, I don't know if they quite got to mini Redis, but there wasn't going to be an exercise to debug a performance problem in MIDI Redis. So Carl told me about this, and I tried using dial9 to go find the problem. And when we get to the end, we will, I was gonna do this live demo, seemed too much hassle, but when we get to the end, I'll show you the actual output of asking dial9 with Claude to fix the P99 issues in MIDI Redis. So for a while, I've been hearing people say things like, I wish I could understand what Tokio is actually doing. Like, where is the time actually going? And the problem is that even with the metrics that Tokio produces right now, it's actually pretty mysterious what's going on. Because to really understand what's going on, you have to go to pretty extreme measures. And I've seen people do this. Like you have to add eBPF to trace the Tokio functions, and then you can actually figure out what the problem was. Or you run your application with perf_sched to record exactly when the context switches are happening and figure out what's going on. But this requires a lot of wizardry and skills, and at AWS you definitely are not allowed to just do this in prod. But it seemed like there should be some way to actually build a tool that can pull in these data streams, a tool that you actually could run in prod to be able to answer these questions. And then a few months ago I got a DM from someone asking for Tokio help, and they were trying to ramp up Rust traffic to a service at high CPU, it didn't work, you know, blah, blah, blah. And I was actually really excited to help them because unlike a lot of the people who come to me, they actually had every Tokio runtime metric. They already had all of them. But the metrics they had did not make sense because it was saying the runtime was pretty much idle, while at the same time the queues were really long. It just, something was clearly off. And then I think is sort of the problem with a lot of the metrics that we can get today, which is that they tell you that something is clearly wrong, but they're not necessarily going to tell you what you need to do to make it better. And I had a hypothesis, but in order to convince a team to go change their service, it has to be really convincing evidence. So I said, give me a few days. I have an idea for a thing we can build that I think will help. And that ended up being the first version of what eventually became dial9, which is a tool that writes events that Tokio produces into a compressed binary format that you can analyze later. There's a lot of systems today that do similar things or try to solve similar goals of understanding what Tokio is doing. But a lot of them solve for a different goal. I really wanted to build something that from day zero was a thing that was designed to be run in production, if not on all your hosts, at least on a subset of them. Because the reality is, for a lot of problems, they're very difficult to reproduce outside of prod. For the AWS service, it only happened when their host was connected to 5,000 other hosts. They don't have 5,000 hosts in their beta environment to reproduce this problem. So I started by writing this compressed binary format that makes it extremely cheap to record events, like 25 nanoseconds, 5 to 10 bytes to record an individual event. And something that was simple enough that you could parse it in 100 lines of JavaScript with no dependencies. That will become important why in a minute. And once I had that, it kind of spiraled from there. So now dial9 gets Tokio events, profiling data, Linux kernel events, and tracing spans. And each of these is useful alone, but I think they're a lot more useful when they all come together in the same file. So let's get back to that AWS team that sort of got this whole thing started. This is the actual trace file from their actual production host. And I'm gonna use it to walk through what you can see. At the top here, this is one of the workers. Each of the rows is a worker. And you can see the blue bar. It's actually about 10,000 tiny rectangles that are all squished together with a few gaps in there. And each one of those rectangles represents a pole, like one future making incremental progress. And one thing that I think is cool here that you can see already is that there's little gaps. The gaps are when the IO driver turns, gets new events from the kernel, and then you can see at those instances the yellow sawtooth line, which represents the queue of this worker, spikes back up, and then the worker goes back to processing data again. And you might be wondering, I thought Tokio was a work stealing runtime. Shouldn't another worker be stealing work from this worker that's clearly extremely busy? And Tokio did attempt to do that. But the problem is this very large red box, which is kernel scheduling delay. Basically, Tokio attempted to start another worker, but it did not actually start for about another 18 milliseconds. And this is very obvious, like looking at a trace in this way. You can imagine looking at Tokio runtime metrics. This would not be clear. In this case, they had 16,000 operating system threads that were contending with their 48 Tokio workers. But you can see how it takes some convincing to be like, no, you really, if you want this to work, you really have to isolate these things. It simply will not work unless you make serious changes. And that's what I'm attempting to get here. So what exactly is dial9 capturing right now? We have pull events, we have wake events, we have the workers when they park and unpark, we have CPU samples both for when the CPU is running, but also, and this is I think very important, for when it stops running. So when the kernel decides that your program is not going to do any useful work and it's going to run somebody else. And of course, all the regular Tokio runtime metrics. Each worker queue, the global queues, all that stuff. And very recently, tracing spans. So we'll also pull in what tracing spans were active when your code was actually running, which makes it much easier to figure out which poll this is in your application. And the trace file is open-ended. You can define your own events, including your own events that schemas are only known at runtime. So I'll show a few things that we found with this data so far. One of the first things I did building dial9 is build a little app that I could load test, instrument it, and sort of see the results. And as I ramped up load, every single time, something very strange happened, which is that all of a sudden, I got these like 100 millisecond pulls, had no idea why. And eventually, once I got kernel stack traces into dial9, it became really obvious. I think that's probably too small to read on this slide, but what's happening is that at the nth connection, the kernel needs to resize its table of file descriptors, and it turns out that this works very poorly under load, and it will block everything for like upwards of 100 milliseconds. Anyway, it's actually a Tokio issue about this from 4 years ago, for when Carl discovered the same problem via, again, one of these somewhat arcane methods. I think he ran his program with strace and spotted this kernel resizing and realized what the problem was. Did not fix the problem, but anyway, the fix is actually to pre-warm the file descriptor table. And once you do that, everything works much better. So I want to step away from this viewer here, the obviously vibe-coded JavaScript viewer, because I don't think this is the way that people are going to use these in practice in real life. I think it's useful to see the data visually, but it's also somewhat limiting. From the beginning, I wanted dial9 to work really well to be analyzed programmatically. So the data is files that are simple to analyze with little scripts. And the information in the viewer is a lot. I showed Carl the viewer, and it was not immediately obvious to Carl what was going on. So if it's not obvious to him, I think it's suffice to say there's just a lot of data. And a lot of the real life analyses are more complex. But because the traces are files, and because the files are not hard to parse, you don't need genius algorithms. You just need a few scripts to ask specific questions. And you know who's good at asking a few scripts to ask specific questions? Regardless of whether you think AI is good or bad or we should be using it or not, the fact remains, if you want to write a few small scripts to analyze a file and generate a visualization, it is extremely good at it. So let me get back to mini Redis. I'll give a quick explainer about what the actual problem was. because the I/O was already ready, you basically ended up compressing many individual events into a poll, which is good for throughput, but completely destroyed P99 performance because you effectively handled many events at once. Anyway, the problem I think is less interesting than the fact that given the trace file, an agent had no problem not only immediately finding the problem, but also fixing it, testing it, and finding a measurable improvement. This problem is somewhat subtle. Like, it was not immediately obvious to me that putting this yield there was going to make a big difference. So, how much does this cost? Why can I run this in prod right now? And the answer is not that much, depending on what you're doing. Emitting an event at dial9 costs about 50 nanoseconds, which is not a lot. So if you pull for 10 microseconds, you get 50 nanoseconds on each side, a little bit of profiling data. The point is, it is measurable. But if your application is not doing millions of polls, it might be very hard to measure it. In mini Redis, which I think is sort of a worst case scenario, it did make P99 25% worse in the single threaded case. But if you go to 4 threads or 8 threads, it becomes, you can't actually see it anymore. I think it's also possible to do tail sampling, and there's a lot of other ways that we can optimize how much it costs to get these events. But in real, actual applications that AWS have used it, they have not been able to measure a difference for their workloads. It also produces a lot of data, unsurprisingly, maybe like 100 gigabytes per host per day, which again, is not an absurd amount, but it is also not a tiny amount. Anyway, thank you for watching and listening. I think we'll try to do a little workshop tomorrow where I can answer lots more questions, do demos and stuff, so we'll see when that's scheduled. Integrating dial9 is pretty easy. All you have to do is switch from Tokio main to our main, and if you read the docs, there's a way that you can, with an environment variable, have it 100% off, not touching your code at all, or if you start off the application with an environment variable set, it will be enabled, so you can sort of safely change your production code to do this. And yeah, thank you very much for listening.